This is a demonstration of a robust calibration technique for 3D MEMS accelerometers. The rotary stage unit is outfitted with 2 servo motors that allow the vehicle inertia monitor device to be situated at 14 different orientations. This is the non-calibrated accelerometer at this point that has not been calibrated. You'll notice that the z-axis here says 1G, which is actually correct. But when looking at the other orientations of X, Y, and Z, you'll see that the values, specifically in this instance, this should really be minus 1G, but it's minus 1.12, 1.16 on X, and then minus 1.17 on Z. So there is significant error of the accelerometer information when it is not calibrated. The method of the calibration involves Jacobian error estimates along with a Hessian error matrix to be able to resolve and calibrate the X, Y, and Z axes without requiring the rotary stage unit calibration test apparatus to actually be level. The technique uses minimization of errors received from X, Y, and Z corresponding to just one input, the gravitational constant of the Earth. The technique involves gathering X, Y, and Z information for each of the 14 orientations. This will show how the calibration occurs. The servos step through casted orientations of each location of the inertia monitor device, and upon completion, the raw MEMS information of X, Y, and Z that is measured from the non-calibrated accelerometer is saved. This raw information is saved to a MEMS file. The cal file is created, and then the cal file is read. You'll see here that these are the scalars and offsets in order to calibrate the 3-axis accelerometer. The calibration matrix compensates for cross-axis coupling between the axes. Once the calibration is formulated, it can be flashed to the device. This is all occurring across CAN bus, and then after it's calibrated, you can now review the accuracy of the calibration in the orthogonal mode of the GUI capability. So now you'll see that the x-axis is now at 1G, y-axis is now at minus 1G, x-axis goes to minus 1G, z-axis is now at minus 0.1, or minus 1G, and then the y-axis is at 1G also. So this calibration technique will be extremely useful for doing temperature-based calibrations in which the MEMS accelerometer drifts significantly during temperature variances. Now this apparatus can be placed inside of a temperature chamber, and the temperature chamber can be set to a low temperature, a nominal temperature, and a high temperature. And the S-scalar matrices and offsets of each axis can be linear interpolated between those temperature calibration matrices based on the temperature read from the internal gyroscope of the vehicle inertia monitor itself. Thank you for watching.